Okay, welcome back. We have now our second part of the tandem talk with Professor Kaiser, historian of physics and physicist. He got, in fact, in 2000 his PhD at Harvard University in history of physics and in physics, and since then he is at MIT, where he became in 2011 professor for the history of science in the program of Science, Technology and Society, and since 2015 he is professor of physics at MIT as well. And he received a number of recognitions, prizes and awards, including the David Prize for his well-known book, How the Hippies Saved Physics. So please, the stage is yours.
Yeah, it's not too dark, you can still see, I hope. All right. Thank you so much, Flavio, and I want to thank all the organizers. It's a great pleasure to be here. It's a very interesting and unusual kind of conference, and I'm very excited about the discussions that I hope we'll get to have together. So as you know, my assignment was to be to wear my historian's cap and try to help put some portion of the work of the sort that Chris Fuchs described for us into something like a historical context and what might come out of that discussion. And so I wanted to start with some reflections on sort of different kinds of relationships we might consider between something like the history of science, history of physics, and research practice in physics. And then the bulk of my remarks will be in the second part. What are some of the ways that I've tried to make sense of the kind of longer course of research in and around quantum foundations that would help foster more recent work in quantum information, and then finally some brief remarks at the end about what are ways that both historians and physicists might make use of the past in making arguments or charting paths in the present and for the future. So, Chris started with some brief thoughts about what brought him into the work that he has been able to pursue, and I thought I would just very briefly try a similar kind of start. My story also goes back to when I was in junior high school and high school. In my teenage years, I was just a terrific fan of popular books on modern physics. Some of my favorites that I remember very clearly from the time, books by John Gribben, by Heinz Pagels, I think is a shared favorite, I think, for both Chris and I. And I just devoured these. I really couldn't get enough. I also discovered older, marvelous books, popular physics writing didn't start in the 80s. But it turns out I later came to realize that books of this sort, the books that were being published in the mid 1980s, especially in the United States at least, really stood out in a couple ways. First, they started to actually sell. So this was a phenomenon where popular science writing, again, at least in a US context, was beginning to actually really be commercially successful instead of unusual hits that would break through. And even more interestingly, there was a trend that I wasn't even aware of, though in hindsight, I think had a big impact on me. A lot of these books were finding a larger audience by explicitly adopting a kind of historical approach. That these books were very good, as the earlier generations were, of finding very telling metaphors and analogies, not using mathematics to try to get many kinds of readers interested in great challenges of quantum theory and the Big Bang and so on. But there was an emerging trend, a real pattern by the mid-'80s, just when I was encountering these as a young person, trying to use sort of human stories, something like a historical approach to motivate this quest, this long-standing journey to understand, and that really hooked me. There's an interesting book by a literature scholar looking at some of the kind of narrative, rhetorical strategies of these books of that era that I have enjoyed. And again, in hindsight, I was already hooked on physics and became sort of entranced by a kind of human side of the research enterprise through these books. That's not to say that these books are marvelous history the way professional historians today would want to conduct it, but there was a reorientation in how we might think about physics in trying to describe the excitement for very broad audiences. And that really had an impact on me, and that indeed helped drive me toward the history of science as an actual field, as something that could be done professionally and full time. So that was the kind of history and physics in brief. This is what helped convince me to try to pursue a career in history of science, even as I was still engaged in physics. So I went to graduate school and I was studying both theoretical physics, early universe cosmology, as well as history of science. And I found even then that there was some kind of relationship between my physics studies and my emerging historical research, not a direct one, but a kind of indirect one. And again, partly this became clearer to me later in hindsight, that a lot of the questions I was really curious about as an historian were kind of inspired or triggered by some of my physics research or broader questions. But with some distance. I wanted to have a kind of a wall between the physics research that I was so excited about and working very hard on, and the kind of historical work I would do. So there would be some kind of separation between the two. For example, even in terms of time period, I tried not to study episodes, historical episodes, that were so recent they could have involved sort of the advisors of my advisors, right? To keep a little kind of separation. And there were two main reasons. One is maybe very obvious for this group. I wanted to be careful about anachronisms, how we approach questions today in a whole range of fields. I didn't want that to color too much my efforts to make sense of what people were doing at earlier times and places. There's much more work and evidence and so on that's come out since then. So we think about things one way now in various areas of physics. I didn't want that to kind of cloud or again, be kind of an anachronism when I went back to try to understand what physicists were doing in earlier periods. And the other one was a lot of my interests as an historian were not only in conceptual or intellectual history, but also in social and institutional history. And that involves things like annual reports, letters of recommendation, tenure committee reports, some stuff that can get rather sensitive and even confidential. And I thought it doesn't make much sense to be trying to dig into that of the people that I otherwise want to learn from and work with directly. So I had this kind of guideline about the historical project had some kind of attenuated connection to my interest in physics, but not super close. So with that in mind, I began asking questions as an historian of a similar bent, even as I applied it to different examples. And the main driving question is, how and why have various research questions or tools and techniques come to be legitimate within the physics community in specific times and places? Not who got the answer right first, that's also can be interesting, but really, when did that even appear like a legitimate question? When was that something when a substantial body of people could say, I'm going to work on that, even if they disagree on the answers at the time? And so the questions I was curious about often were related to the areas I was interested in physics. So my first book was on the early dispersion of Feynman diagram techniques in high energy theory and eventually into many body theory and condensed matter and so on. So how does a new way of dealing with elementary particles, for example, how does that come to seem second nature for a community when it starts off looking very strange and possibly wrong? And likewise, some of this early historical work when I was just still a grad student or soon after, interested in things that would be a kind of precondition for the areas of physics that I was most excited about for my own research, like shifting ways of dealing with even classical general relativity, different kind of conceptual tools or techniques, the emergence of whole new fields of study like particle cosmology, in which I was being trained as a physicist. So the question of when do those things emerge as sort of coherent or even legitimate questions, as opposed to who got this answer right first, that kind of thing. So that's a history of physics. I was then, for a next project, a more recent book, I was interested in a kind of early history of Bell's theorem and quantum entanglement, who paid attention to Bell's theorem before sort of we all realized we had to in many, many areas of study. And so that became this book that Flavio mentioned, How the Hippies Saved Physics, with a sort of obnoxious title. I was guided, I really want to pause and say, I was led into this work by really marvelous, essential work that had a big impact on my own thinking, both by Louisa Gilder, a lovely book called The Age of Entanglement, and of course, Olival Friere's book, The Quantum Dissidence. The book came out a bit later, but many of the key findings were coming out in really major, essential articles that Olival was publishing along the way, and so those were a very helpful guide for me. But again, the question, as I went into it, was, when did people come to take questions about, say, Bell's theorem as legitimate or serious physics? What were some of the processes that had to change for that to happen? In the process of that, I began then digging into, as all had as well, and Louise, some of the history of some of the earliest experimental tests of Bell's inequality. The Clauser-Friedman experiment, published in 1972. Here's a very young John Clauser duct taping together his apparatus at Lawrence Berkeley Laboratory in the early 70s. And then 10 years later, of course, the marvelous and famous experiments by Alain Aspect and colleagues near Paris. So while working on the historical project, I was learning about who was putting those experiments together, what did they think they were out to test. An early discussion that came up even before Clauser and Friedman did their first experiment about what we would now call loopholes in various experimental tests. So that was an opportunity as an historian for me to learn more about the kind of evolving way of interacting with or thinking about Bell's inequality, both theoretically and experimentally. And of course, in the book, I was looking at some other folks further from those centers who were also among the earliest to be really interested in Bell's theorem and did interesting work along different directions. They called themselves the Fundamental Physics Group. They often met at the Esalen Institute in Southern California, or sort of near San Francisco. And so these were some of the other sort of people in and around this swirl of attention to Bell's inequality, and indeed the first experimental tests in the sort of mid to late 1970s. And then I had this slide while Chris was talking. One of the outcomes of that was this really kind of convoluted, I think really interesting story that led to things like the no cloning theorem. And part of the impetus, by no means all, but part of the trigger for that was a very interesting thought experiment by Nick Herbert, a member of this rather playful group. That's Nick back there, in fact, in that photograph, where he came up with a series of thought experiments to try to use entanglement to conduct faster than light signaling, just indeed as Chris had said. One example he wrote up was called Flash, First Laser Amplified Superluminal Hookup. He's very playful. He'd released this preprint from the Notional Science Foundation. That's not a typo. It wasn't meant to be the National Science Foundation. He was just working basically at home and this was his P.O. box. So he was on the margins, but thinking hard about what we would now call quantum foundations. And indeed, as I talk about in the book, and as Chris relayed as well, that helped set in motion a series of responses, extremely creative and important responses, and very foundational work by people like Wouters and Zurich, Deeks, and Girardi, and so on. So those are the kinds of questions I was after in writing this book. As an historian, how do these questions come to seem sort of legitimate questions within the field? And then something really quite remarkable happened. The book came out, and then I had just hired Andy Friedman, or I was able to welcome Andy to MIT as a postdoc. Andy had just finished his PhD on observational astronomy, so he was studying with a large group light curves from supernovae and trying to recalibrate how we might worry about things like late universe acceleration. He was coming to do a postdoc with me in astrophysics at MIT about, again, dark energy stuff. He also was very interested in the philosophy of science. We're going to do fun stuff. He read my book for fun because it had a weird title and he was about to switch over to MIT. What's all this about? Just as he was leaving grad school to come to MIT, he had dinner at a pub near Harvard Square called John Harvard's with his good pal from graduate school, Jason Galicchio. Jason was separately already thinking about Bell's inequality and various tests and so on. He had a different motivation. Andy was about to move all the way from Harvard to MIT, which feels sometimes like a very large transition. But Jason was about to go from Harvard to the South Pole. He was actually really going to start traveling the world. Jason's first postdoc was with the South Pole Telescope collaboration. And in particular, his job was to do what they call the winter overshift. So he was an astronomer to make sure the telescope was working even when there was a sort of skeletal crew. The joke among astronomers is that's a really great gig to have the winter overshift because you get paid a lot of money for one night's work. It's just that night lasts for 6 months. That's South Pole humor. So while Jason was in Antarctica and Andy was 2 doors down from me at MIT, we went back to these questions about Bell's theorem and what kinds of experiments have been done so far. Can we now use what a different community, astronomers and cosmologists, have learned in the intervening several decades about the causal structure of the universe on very, very large sort of cosmic scales to revisit questions at the center of tests of Bell's theorem? So while Jason was at the bottom of the Earth, we managed to write a paper together to propose this. And then to my great good fortune, we were able to describe this proposal to Anton Zeilinger during a visit to MIT. Anton and his group was already deeply immersed in this sort of so-called third loophole. It's often called the freedom of choice or measurement independence loophole. And we had a different kind of take on that, really growing out of, at least in part, the fact that I had been immersed in some of this history and he'd read the kind of historical book for fun, and that catalyzed new discussions for us as physicists. So once Anton thought this was a fun project as well and signed on, then things moved rapidly. They often do when Anton signs on, right? So we were able to build this collaboration right here at IQOQI, as well as MIT, Harvey Mudd, some colleagues at JPL. We got my colleague Alan Guth involved, as well as some of the just amazing physicists here in Anton's group. And with generous support both from the NSF and the Austrian Academy of Sciences, we were able to now start doing new kinds of experiments that were triggered not entirely, I want to be clear, but at least in part, by this historical effort to understand some of the earliest experimental tests and early ideas about loopholes and how they could be addressed experimentally. And I can't help but show these photographs every time I get these, no matter what the topic of my talk is, I show the same slides. I can't help it. Here's Johnny, there's Johnny, here's Johnny. So we were able to do a pilot test here right in Vienna, in fact, shooting entangled particles off the roof of this building and collecting. Alice's station was in the top floor of the Austrian National Bank, which is a further indication of Anton's charm, that he can talk his way into. He can get young physicists badges to bring their lasers and telescopes to a highly secure building after hours. That's what it takes to do these experiments. And likewise, Bob's receiving station a kilometer in the other direction, a university building. So we were able to do a kind of pilot test, and then because of that, we were then able to go and really zoom this up to the universe with these amazing telescopes at an observatory in La Palma in the Canary Islands. Here's Dominic, who's also here, and Thomas Scheidel and the gang. So the point is, we then could do another even grander experiment, these cosmic bell tests, finding, again, very substantial violations of this CHSH inequality, not terribly surprising, but now being able to make quite strong statements about constraints on non-quantum mechanical alternative models, certain kinds of basically locally invariable models, that if those were at play to account for the experimental correlations we measure here, they had to have been put in place at a cosmically distant time, about roughly 8 billion years ago over there, right, in the universe, and not any old place. In fact, we had ruled out these kinds of locally causal explanations of our data from all but 4% of the space-time volume of the past light cone of our experiment since the dawn of time. One of the great things about being a cosmologist, we say things like since the dawn of time, and we kind of mean that. So this was a quick example that I couldn't resist showing here in IQOQI of where there was a kind of history for physics that I didn't anticipate at all, that was by one of the greatest adventures of my life, to be honest. It was just an amazing opportunity that spawned some new physics and ongoing collaborations that came unintentionally from my work as an historian trying to dig into this topic of Bell's inequality and early tests. So clearly, I'm hopeful that there is indeed a room for history for physics more broadly, and that was just a kind of prelude to then say, what might that look like, and maybe what are some cautions or concerns to think about as well. So now let me turn to my actual charge, what I was asked to talk about. What might an historian do trying to take something like the material that Chris shared with us just earlier? How might historians try to contextualize or make sense of the kind of rhythms and the time periods over which this very exciting work has emerged? And in addition to Chris's book, which hopefully you, if you haven't had a chance to look at, I encourage you very much to look at. Some of his more recent papers on archive, I just had a terrific time reading these, and I really enjoyed them. And as Chris himself has said, both in today's talk and in some of these writings, that it seems like a reasonable way to mark the kind of launching of this new field called quantum information in the earlier mid-90s. And he points to this great paper on the first quantum teleportation protocol by Bennett and collaborators. I think that makes sense from my understanding as well, as a kind of marker for something new happening in the field. But as Chris, again, emphasized for us today and in these really quite lovely writings, there's a much, much longer historical lineage. And so going back to some really inspiring ideas by John Wheeler and gathering a group together to chew on these things really quite early when this was not at all common. And of course, going back even further, and I want to just underscore, I especially for the historians in the room encourage you to read Chris's paper on Notwithstanding Bohr. This is a remarkably historically careful study of lots of very obscure Bohr writings. I thought I knew a lot about Niels Bohr's writings, and I was amazed by the things that Chris had found for this. So a genuine engagement with historical sources for the purpose of thinking through challenging questions today, and also, of course, Wolfgang Pauli. So this begs the question for the historian, if a lot of the key kind of germinal insights were available in the 70s and 80s, let alone in the 20s and 30s, then why do we have this field emerging in the 90s? So I set that as my task to say, can we account for the kind of rhythms of this if there are ideas and concepts and inspiring teachers and leaders dotting a landscape beforehand? Why had this field not coalesced until much more recently? And that's consistent with other ways of marking the timing. Many of you might be familiar with this kind of plot. The citations to the famous Einstein-Podolsky-Rosen paper over time, published in 1935, and then basically no measurable reaction from the worldwide physics community, if measured at least by citations. We see some uptick of some kind of early plateau by the late 70s through the 80s. I think very consistent with the other timing that we get from Chris's writing, and then something clearly happening quite qualitatively different by the mid to late 90s. Another marker that I think is in line with the timing we get from Chris's writings. So when I, as an historian, when I try to make sense of these kinds of quite dramatic ebbs and flows over nearly a century, not just months or years, then I start to think about kind of longer traditions of training new physicists and of making judgments about what's going to count as significant work in the classroom. So some of this material I'll talk about today is from a book that's going to come out, a book of mine that will come out in the spring. Some of it comes from the work on the hippies book as well. So everyone in the room, I'm sure, recognizes that back in the early days when quantum mechanics was just being forged by many, many hands, many of members of that founding generation were quite convinced and quite prolific about the fact that this brought with it a series of philosophical challenges, or at least subtleties. One of Niels Bohr's favorite phrases, other than using the word notwithstanding, was there's a general epistemological lesson of the quantum. So he'd write that over and over and over again. And now they would point to different philosophical traditions. They'd say something new something philosophically rich is going on here, and to best make sense of it, they would point to different inspiring philosophers, whether it was Kant, Ernst Mach, in some cases for Wolfgang Pauli, even psychoanalysts like Jung. Schrödinger wrote interesting things about Eastern kind of spiritual traditions. But what's important is that it was an explicitly philosophical job as well as one of mathematics and experiment to their minds. And that same idea that this is a philosophical challenge animates many, many of their early pedagogical writings, the books that were written, that were either used in classrooms or written intentionally as textbooks. They'll have whole chapters on quantum mechanics and philosophy as the chapter title. Even, again, from these differing schools, they'd agree that this is at least something philosophical we must sit with. So there's a common story in the historical literature going back to, again, very classic work by Catherine Sopgood, Gerald Holton, Sam Schwaber, that somehow the story played out very differently within the United States. And the United States, at least to summarize their work briefly, that this was a much more pragmatic, unphilosophical approach to quantum theory, even in their account in the 20s and 30s. And that was what I assumed must be the case as well, until I began looking into this a bit more thoroughly. It turns out some of the earliest pedagogical efforts to train PhD students in the then brand new quantum mechanics within the United States were just as overtly philosophical as many of these examples from continental Europe. They were different philosophical traditions, but they weren't let alone anti-philosophical. Many of them pointed to the Harvard low-temperature physicist Percy Bridgman, who had an idea he called operationalism, which is certainly related to a kind of positivism, some subtleties. In the earliest textbook published by US-based physicists by Condon and Morse, came out in 1929, it's quite early on. They have lengthy discussions of Bridgman's operationalism as a way to make sense of the new challenges of quantum theory. Edwin Campbell at Harvard also appeals to this explicitly, Harold Urey. Meanwhile, there's a separate tradition starting to take hold with a very young Robert Oppenheimer, who had just come back from a kind of European tour, a postdoc essentially, and began teaching a wildly popular course on quantum mechanics to graduate students at Berkeley and to Caltech. It was so popular at one point, there was a grad student who went on a hunger strike because Oppenheimer at first refused to let her take the course for a fourth time. And he relented. She was so desperate to take this course again, so she did. So he was becoming this sort of magnetic lecturer on the new quantum mechanics, having studied with people like Max Born and so on for his postdoc. And Oppenheimer's lecture notes survived. They were carefully written down by a student and hectographed, a kind of pre-mimeograph technology. They were sold. There's all these records in the Berkeley Physics Department, sold for like $2.50 all over the United States. Copies are still in libraries. And he really sat with some of these kind of philosophical challenges. He would often reconstruct the kind of Einstein-like objections to quantum theory that came out of these Solvay conferences. What if, could we elude the uncertainty principle? Oppenheimer thought we need to sit with this stuff as well as learn to manipulate the Schrödinger equation. Because for Chris's sake, I found it interesting to go back to Condon and Morse in this book from 1929. This is certainly not cubism, but I thought it was a nice, interesting kind of engagement with these ideas. After going through the standard solutions for the hydrogenic wave functions of an electron in an unperturbed hydrogen atom, they pause and say, let's be careful here. They're drawing again on operationalism. They say it's meaningless to attribute quantum numbers like L and M to an unperturbed hydrogen atom, no matter what form the wave function takes. So they're already trying to distinguish between there's a wave function, a way of organizing our knowledge about the system, but not attribute it to reality itself. We don't have to follow their line, but that was in their textbook as part of their discussion of how to solve the Schrödinger equation for the hydrogen atom. Campbell writes, there are philosophical difficulties in quantum mechanics. These are a brute fact, he says, which cannot be exorcised. We can't wish them away. This is what's going on in many leading classrooms across the United States, again, in the very late 20s and early 30s. My favorite example beyond that comes from a series of notebooks in Caltech's physics department. They're called the Bone books. These were kind of communal notebooks held by the graduate students in physics for 40 years, between 1929 and 1969. Think of all that changed in between. And the books were a place for the grad students to narrate how they had prepared for their general exam. They had an oral exam, not a written exam. And so they would describe for the students who would come after them, how had they prepared and what were the questions they were asked. And they become eventually very witty and kind of student humor about boxing matches and imagining the sort of the challenges they face in the oral exam. But you can see the questions they were reporting they were asked on their exam in the 1930s at Caltech. One of them is, what's the interpretation of the Schrödinger wave function? Does the equation describe the rate of change for all time? Already asking about what would come to be called the measurement problem. Is there some discontinuous kind of collapse behavior of the wave function, and talk it through? Discuss the nature of observation in quantum mechanics and classical mechanics. This is not anti-philosophical work here at Caltech on an oral exam in the 30s. And likewise, there are written exams, the more written formal exams for PhD advancement for many, many departments around the country, written exams, textbooks and textbook reviews. The picture that emerges, at least as I see it in the United States, looks more like the pedagogical situation in Europe than distinct. The philosophical approaches are different. There are very few neo-Kantians spouting that approach in the US, but they're not shying away from the fact this is also an overtly philosophical challenge, 1920s and 1930s. Okay, then something very abrupt seems to happen in those same kinds of sources, kind of remains traces of the training of young physicists soon after the end of the Second World War. My favorite example is from MIT physicist Hermann Feshbach, who finally says, enough with this musty atavistic to-do about position and momentum. And this is the era that comes to be called shut up and calculate, right? The main business is to train students to really work through increasingly elaborate calculations as physicists are busy applying the formalism of quantum mechanics to more and more and more types of phenomena across the domains of physics, to what would soon be called atomic and molecular, as well as nuclear, as well as many-body in many areas. The textbooks that are now written by US-based physicists in the 50s and 60s are now being praised in the reviews for avoiding what they call philosophy. Instead of holding up being this is particularly clear exposition of Percy Bridgman or whatever else, now the books are praised for not engaging with that at all. and go back to those Caltech bone books. Remember, those are continuous from the late 20s to late 60s. And you see these funny entries in the late 40s, early 50s, where students who had studied the previous essays to learn to prepare for their own exam now feel like something dramatic has changed. One of them says, the effort invested in analysis of paradox and queer logical points was of no use in the exam. So the student had been reading the accounts of these kind of philosophically engaged earlier examples, says forget it. Another gives advice to his fellow students, just memorize and rehearse the stock problems, give what he says the usual spiel. They're not being asked in the oral exams the same kinds of questions as before the war, and again that's borne out by other written examples, the written out more formal general exams at other departments, the homework problems when we can find them. It really looks like these sort of open-ended essay question style format is getting rapidly replaced by a standard coterie of calculations. Yeah, Danny.
Yeah, when I was a student, which was in the late 50s,
yeah.
There were two standard textbooks.
Yeah.
One was by Schiff,
Yes.
which was very good calculations,
Yeah.
very good homework problems.
Right.
But no discussion
Yes.
of any kind of philosophical. And the other was by Bohm.
I'm going to pause only because I have this. Clearly, you've stolen my slides. This is exactly it's perfect. Please go ahead. Yeah.
Rather than interfere with what you're going to say.
Yeah. Go ahead.
Let me just say, we used to say that there was no text in Schiff and no equations.
Right. No, it's exactly. And so perfect setup. So I didn't pay you to say that, but that was perfect. Thank you, Danny. No, that's right. And so in fact, that's an example I find very interesting. So before we come to the textbook split, what might account for that shift? Not the Leonard shift. What might account for that shift? Why were those students at Caltech caught by surprise when they studied the examples of the older exams? So you might say, well, there were no more open questions in quantum mechanics. That's a joke, right? We know that wasn't true. Amazingly important work was just about to start coming out over the coming generations. So the philosophy didn't disappear because there were no philosophical questions left. That's obviously not what happened. There's a really interesting line of historical work, familiar, I'm sure to some, if not all of you, by historians like Peter Gallison and again Sam Schwaber I mentioned. Says maybe World War II really was causal in this shift. It wasn't just a historical interlude. That when many physicists and engineers and chemists and experts of many technical fields got so involved during the Second World War in defense projects, nuclear weapons, radar, proximity fuses, that there was a need, as Sam would always say, to get the numbers out. That to pause about these kind of interesting, juicy epistemic questions, there's no room for that. There's a war on, we've got to get numbers out. And you think about these isotope separation plants, city block long kind of industrial operations that physicists found them in, that has a plausibility to it. And yet, as I'd be glad to say a bit more of in the later remarks, that doesn't quite really capture it either. There's a bunch of counterexamples that are sticky, that I think it's worth pausing over by lecture notes by people like Lothar Nordheim and Epstein and Hill and others that persist from this later period. So I don't think we can say it's World War II made everyone, at least in the United States, a pragmatist. That's a little too quick as well, I think. A different line or related line of historical work by people like Paul Foreman in this classic essay in Historical Studies in Physical Sciences, or Bill Leslie's book, says, it's actually a Cold War story. The way physicists were entering the field, especially in the United States after the war, was different enough from the 30s, and that will account for it. That somehow, if you're working for a government lab or an industrial research laboratory, again, the plausible argument is the students didn't have to worry about, psi-epistemic interpretations or whatever. I should say, in 1953 was the first year in American history where more physics PhDs took jobs in industry than academia. There really was a transition going on in the employment patterns. But that's an empirical question. For reasons I'll mention briefly to come soon, the United States was obsessed with tracking every single physics student and producing basically print-based databases. We have an enormous amount of information about who was entering the system and where they were getting employed. Then you can try to correlate that with the style of quantum mechanics they encountered in grad school, and there's no correlation whatsoever. So I don't think we can say I don't think it's only a story about patronage or employment demands. And that makes me then come back to this question, which I've always been interested in, about teaching and training, and sort of what does it take to make generations of young scholars, and how is that responding after the Second World War? So I stare at this curve a lot. Some of you might have seen this in some of my previous writings. I write more about it in the new book. This is showing the number of PhDs in physics per year in the United States. I should have said earlier, my examples come mostly from the US, not because I'm trying to claim that's the most important or the only setting to study. Far from it. It's the setting I happen to know most about. And I'd be eager to hear and have discussion about disanalogies in other places as well as similarities. And so I'm presenting a US-focused story because that's where I've been in the archives most. So you can see these remarkable patterns here. Here's the end of World War II, lightning fast growth in the production of physicists per year, again after the launch of Sputnik, and then a really precipitous fall by starting in the late 60s, early 70s. Just to be clear, every field of study in the American Academy was growing exponentially after the Second World War. There's something called the GI Bill in the United States. So people who had served in the war, service members, could have their higher education largely paid for. Huge, huge social change. So even as every field grew, physics grew with an exponent twice as fast. And likewise, it's not just a kind of baby boom demographic effect. In fact, the share of the US population between ages 25 and 29 was actually falling just when these PhD numbers are going through the roof. So it's not just more young people entering higher education, it's not just because every field was growing. There's something about physics is growing even beyond the other more general patterns. And in fact, that pattern looks more like a speculative bubble, like a stock market bubble, than like any kind of demographic shift. And it indeed was driven in large part by shifting policies in the United States. Even before the United States entered the Korean War in June of 1950, there were efforts to make sure the wartime mobilization of some form stayed active in case the Cold War ever turned hot. You have these remarkable speeches by members of the American Institute of Physics, the Atomic Energy Commission, saying that scientific manpower, and they almost always meant grad students in physics, are a short commodity like rubber or tin that we have to stockpile and ration, track every single one of these people through. And that led to changes in draft policies during the wars and so on. Of course, that didn't, then this heats up all over again with the launch of the Soviet satellite Sputnik in the late 50s, leading to new policies, new funding, new incentives to get more and more people into physics and related areas of engineering and broader physical sciences. So this curve is being driven not because there are more young people. It's being driven in the United States by very specific shifts in policies and funding and so on. And of course, that doesn't last forever. So again, I'll be brief here. These late 40s, early 1950s shifts in policy come to a really quite abrupt reversal by the mid to late 1960s and into the 1970s in the United States. These are just two pictures just from MIT, the 50th anniversary of which is this coming November. Huge, huge turmoil on campus about the role of the defense spending on university campuses, especially as the Vietnam War was escalating. And now draft deferments were being taken away from grad students, even those in physics in many instances. The role of military spending on campus came in for a very dramatic rethink. And this was coupled with huge federal budget cuts in both defense and education spending. So this starts to feel, again, like a kind of speculative bubble. When things start to fall, they have nowhere to go but down. This slide always I find very chastening. The American Institute of Physics ran a kind of placement service at the annual meetings to try to relate young PhDs looking for employment with employers looking to hire PhDs in physics across all sectors, universities, industrial labs, government labs. You can see even while production was growing exponentially in the mid-60s, there were more jobs on offer than students registered. So the main thing to do if you are worried about your financial future in physics is build a time machine, right? The best time to have been a physicist in the United States was 60 years ago. The balance tips by the late 60s, and look at this. By 1971, you have 53 jobs on offer, at least through this AIP service. And that's not university jobs. It's 53 employers, Bell Labs and such all included, and more than 1,000 PhDs signing up for interviews. That's what a bubble bursting looks like, right? So one of the questions is, what's it like to become a young physicist in these very, very different settings? Here's two photographs of Richard Feynman, both at Caltech. Here he is lecturing to these famous filled auditorium-style lecture halls in the mid-50s, and here he is 20 years later. He's lost the jacket, his collar's wider, and the kid's got the feet up on the desk, right? Something has changed. And there's, like a dozen versus something like 150. Something has changed. So what's it like to talk about the challenges of quantum mechanics in these very different pedagogical settings? That's what has really grabbed me and I've been curious about. So one thing we can do is look at, again, text-based remains of what it was like to try to train grad students during this boom year, during the years when the enrollments were growing so rapidly. So I found about a dozen full-length lecture notes, most of them not previously published, of the same kind of course, first semester quantum mechanics for PhD students. I want to compare like with like. From many, many different departments, well, from roughly a dozen departments across the country. And then I just coded what's the fraction of those lecture notes that was devoted to anything we could plausibly call foundational or philosophical. We can disagree, does that count? But I mean, in gross manner, I think we sort of know it when we see it. And you'll see there's, in the minority of classrooms that had not yet become so large, the enrollments were still on the order of a dozen, which you can reconstruct in various ways, and they had something like 12 or 13, 15% by page count devoted to something like what we might recognize as foundations. And in the larger classrooms, which were by this point still only averaging 40, but soon would become on the order of 100 at places like Berkeley and MIT, you have a fall by a factor of 5 in the page count devoted to these things. Now that's clearly at best suggestive. I'm not telling you that's a great proof, but that's a kind of correlation that goes along with sort of enrollment, pedagogical infrastructure, and an explicit attention to philosophy. And here, Danny, right, is exactly the point you were making as well. We can further mark this by tracing the lives of two remarkable textbooks, the very two that Danny mentioned, by Leonard Schiff, which first published in 1949, simply called Quantum Mechanics, and by David Bohm in 1951, called Quantum Theory. Now there's a lot, again, we're starting out comparing like with like. Both Schiff and Bohm were members of Oppenheimer's group in Berkeley in the 30s. Schiff as a postdoc, Bohm did his PhD with Oppenheimer. They had both taken Oppenheimer's, by then very famous course in quantum mechanics. If you look, though, just exactly as Danny had said, Schiff's book has a very different style on the page than Bohm's. Schiff, in other lecture notes I found in his papers, says on the first day of class, we shall discuss physics, not philosophy, on day 1. Okay. The Schrödinger equation appears on page 21. It took him all of 20 pages to get the Schrödinger equation. And for Bohm, it appears on page 191, right? That's order of magnitude, right? And a book review at the time actually praised this approach, saying that Bohm's book was concise and well-balanced, had this interplay between formalism and interpretation. It was clearly more words on the page than Schiff. And likewise, in a kind of joint review after Bohm's book came out, these were the two obvious ones to compare. And a review in the American Journal of Physics says that on the topics that are covered by both books, it's to the credit of Bohm's book that it gives a clearer and more physically understandable explanation. They both start out as promising ways to teach young students, graduate students, quantum mechanics. And then the paths diverge. Schiff becomes department head at Stanford. He then becomes series editor for the series in which his own textbook had come out from McGraw-Hill. He gets very involved with consulting for the Air Force Office of Scientific Research, helping them to figure out how to disperse funds for physics research projects, elected to the National Academy of Sciences, and just a marvelous career. He died tragically very young, but had a really meteoric rise. And again, as people in the room likely know, and then had two further editions of his textbook come out, both in the mid-50s and late 60s. I'll say more about those in a second. On the other hand, David Bohm's path starts to look quite different. Again, as people probably know, he was hounded during this domestic anti-communism, called up to question by the infamous House Un-American Activities Committee. I won't say more about this because Olival has written just such beautiful accounts of this, both as a chapter in his Quantum Dissidence book, which all of you should rush out to buy, and even more recently in his biography of David Bohm that came out weeks ago, fresh off the presses. So there's much, much more to be said about Bohm's experiences, but this is, as Schiff is sort of rising this marvelous career trajectory, Bohm is really interrupted in a serious way, with an impact on his own textbook as well. His book was never reissued. It was allowed to go basically lapse out of print. A reprint came out decades later, and then he tried to write a follow-up textbook, and I know that because he submitted a proposal to Leonard Schiff's series at McGraw-Hill, so the proposals in Schiff's papers, and this was rebuffed. This is the worst kind of book. It was basically said too much philosophy. So it fell to another member of Oppenheimer's group, Edward Gurdjieff, who'd also been there in the 30s, to then try to make sense of the different patterns that were starting to unfold. He wrote, again, a kind of review of the second edition of Leonard Schiff's book. The book came out in 1955. He says, in expanding the book, Schiff paid even less attention to what we might call foundational or philosophical material. And he says the contrast with Bohm's book is interesting, even amusing. And he says it kind of makes sense why Schiff dropped even more of this stuff. Gurdjieff says, with these subjects like correspondence principle, uncertainty, complementarity, and causality, lecturing's of little avail. The baffled student hardly knows what to write down. Whatever notes the student takes are likely to kind of offend the professor. By focusing on these calculations instead, the student, as Gurdjieff says, is well into detailed algebraic complexities, verifying which he persuades himself means he's learning quantum mechanics. But Gurdjieff says, hang on, remember another Oppenheimer protege, is it necessary, as Schiff does, to leap so rapidly over the philosophical issues raised by quantum mechanics that the student never has a chance to gauge their depth? And of course, he thought that was too quick. Meanwhile, another remarkable document in the Schiff papers was a 16-page referee report by the Berkeley physicist Ivan Wickman, a high-energy theorist. Wickman, originally from Helsinki, but trained at Columbia in New York City for his physics training. And he basically asked, should there be a third edition of Leonard Schiff's textbook? The first two have been so successful. And Wickman says, yes, there should be a third one. And here's why this is such a great book, he says. He had studied the first edition when he was himself a young student. And he has basically kind of Kuhnian answer about why the best thing we can do is just load these students up with more and more creative homework problems. That this is how you learn to become a physicist. It's not a bad answer. It's just telling that this is the direction we should emphasize, he says. He says, I believe the explanation is that Schiff is a very practical book. The reader goes through the book and really obtains a working knowledge of quantum mechanics. He's taken through a number of well-chosen applications, and he's shown through these examples how it all works out. You can actually compute things with a theory. You build up this reserve of problems successfully attacked, and this knowledge can then somehow be used in attacking new problems. And he goes on to say it's better than that when he himself was using the first edition textbook. So I was perfectly happy with his mode of presentation, and it kept me busy. So to prevent these pseudo-philosophical speculations about the true meaning of quantum mechanics, and that's a good thing. Yes, we need a third edition. Okay. So that's another kind of snapshot of different kind of approaches to training grad students in quantum mechanics. Then I wanted to take a more diachronic view, sort of across time, and ask, do these patterns hold up? Again, at least in US-based classrooms. Physicists based in the United States published 33 graduate-level textbooks aimed explicitly at first-year PhD students, 33 books during this period between 49 and 78, so over 30 years, roughly, about one book a year, roughly. If you go through all those textbooks, they include 6,261 homework problems. Actually, they contain 5 homework problems repeated ad nauseum. We can all guess what they were, but there's this huge collection of problems embedded in these textbooks. Then I went through and looked up the book reviews of all of them in Physics Today and American Journal of Physics. Yes, this is meant to be used for first-year PhD students in quantum mechanics, comparing like with like. This mountain behind you is an excerpt I showed before. That's the PhD conferrals per year. That's a proxy for sort of enrollments. Enrollments, you back them up 5 years, roughly. And what I'm plotting here is the proportion of the questions, the homework problems in these books, that calls for an answer using sentences, a kind of short answer or mini essay response, like those Caltech students were asked in the 30s on their exams, versus a sort of strictly calculational way to solve that homework problem. And you can see as the enrollments grow so large, the proportion hovers around 10%, and then when the bottom falls out, there are new textbooks published that have 40% or more essay questions, interpretive questions, called interpretive questions, discussion questions. The format of these textbooks is shifting in correlation with, if not causally driven by, some of these large-scale shifts in the kind of capacity to train new quantum mechanics. George Uhlenbeck, a famous emigre physicist who had settled at University of Michigan, he doesn't like what's happening. He's another kind of old guard who writes another one of these really marvelous book reviews in, I can't remember if it was Physics Today or American Journal of Physics. He says, the physicists have confused what's easy to teach to these now increasingly large classrooms. It's easy to teach the technical mathematical aspects of the theory than what students actually need most, which is some sort of focus on the concepts. This was, again, a minority opinion by the time he wrote that. Then we can look at some more instances of this kind of playing out in very specific settings. So there was a tenure case or promotion review in Berkeley, which at the time was the country's largest department of physics. It was a young theorist who was not promoted. And it turns out it's very hard not to promote someone because it generates lots of paper. And so there are all these departmental reports and department head reports and so on. But why was this person not promoted? He was publishing actively. He was supposedly a very devoted teacher. He was in the lab on Saturdays, which was held up as a good thing at the time. And here's the department head's final reason why this person was not promoted. He was working on foundations of quantum field theory. And this was somehow deemed pedagogically inappropriate. This is the wrong thing to be going on in a department that has 100 grad students, per year kind of thing, or dozens of grad students per year. So he says, it's not the sort of work that can be readily used for PhD theses. The choice of research topic was out of phase with the pedagogical needs. It seemed to our committee that he was not carrying his fair share of the load of grad student research. It was felt he would be not particularly valuable to us since we have a very large number of grad students who must be guided to the PhD degree. The year before that, that same department head had fast-tracked a promotion for a different colleague on the strength of that other colleague's skill at crafting doable problems for PhD students. This is the kind of production model I have to worry about. Nearby in the Bay Area, at nearby Stanford, they're going through a similar kind of push and pull. Not the same, the department was much smaller than Berkeley's, but the swings felt equally severe. This is now the entering number of new PhD students in physics per year in Stanford's department. When the number starts to rise a near 40 per year, the faculty freak out because they used to do personalized oral exams like at Caltech, and suddenly have 40 students to track and they're overwhelmed with giving oral exams. They temporarily switch to true-false exams. You can get your PhD at Stanford at the time by answering a series, not even calculated, true-false, because they could grade those really fast. And of course, that they adjust. Then the bottom falls out around the same time it falls out everywhere. The number of incoming students falls down to 16 as opposed to nearly 50 or 45. And they say, we should have more essay questions now, right? And they do. 40% of the revised general exam during this period now includes free response essays with sentences and paragraphs, nouns and verbs. At that same time, they start a new informal seminar that they call Speculations in Physics, exactly the sort that had gotten that Berkeley professor invited to leave 20 years earlier. Okay, last part of the talk. I'll be much more quick now. So how do we think about the rise of quantum information or the resurgence of interest in quantum foundations in the more recent period, in the, say, mid-90s? One plausible explanation, which is repeated in many, many places, is that there were finally new experiments, that now these questions that had been open for debate for generations could now be settled with the cold, hard logic of good tests. There's a lot that explanation has going for it, but I still find it really quite incomplete. It reminds me, for my fellow historians in the room, about the kind of debates we have in history of technology about whether new technologies drive history, so-called technological determinism. Or do people have to make choices to use technologies in certain ways, so that people are choosing to use technologies, the technologies aren't forcing a particular outcome. I think we want to return to this question of the role of experiments in a similar way. Experiments are absolutely crucially important, and I've just had the greatest time of my life trying to pursue some versions of my own. So I'm not saying we shouldn't be excited about the experiments, but let's be careful what historically we attribute to their role. The experiments couldn't force people to pay attention to them. Right? That's the idea. And we have examples of that, again, from Olivol's work, from Olivol's work and from my own. Let me get back here. Yes, thank you. Going back to Clauser's and Friedman's great experiment from 1972, as Olivol found, and John Clauser shared his correspondence with me as well to show that he was applying for jobs on the strength of this paper published in Phys Rev Letters, glorious first published experiment to test Bell's inequality, and he was hearing back from department heads saying, I'm not sure this is real physics. Goes back to the question, what even counts as a legitimate question, right? He never got an academic position. Ed Fry, who many of you know, again, I learned this from Olivol, at Texas A&M a few years later in the mid-70s, wants to do a new version of a Bell test, use a different source of entangled particles, for example. The NSF said, no, we're not going to pay for that. That's not real physics. Alain Aspec's rightly celebrated experiments in the early 80s, glorious experiments that, as Alain told me, and I think he's written about elsewhere, even after those experiments came out, published again in Phys Rev Letters and to great acclaim, he actually left the subfield and moved into basically low temperature physics, laser cooling, because he at least he perceived a continuing resistance from his colleagues. So the experiments were coming out and they were not forcing a conclusion on the community, at least not right away. Likewise, let's go to citations to Bell's theorem. Here's the early period. Here's when Alain Aspec's experiments are published. You see a jump in the plateau from 20 per year to 40 per year, but it plateaus, doesn't keep rising. If you then do the harder work and look up who are the authors of these papers, they're dominated by people who had already been publishing on Bell's inequality before Aspec's experiment, and they write more papers per year. So there's a kind of an expansion of the field, but not a magnet to gather many, many more students into the field, okay? So I come back to the curves like this, the enrollment patterns. We know that in other periods, when there's this very rapid reversal of fortunes, this can have a big impact on the subfields, the distribution of effort within physics. Again, this is a US-based example. I'd be curious to hear comparatively. So during that first plummet, this crash here, within a 2-year window, there were twice as many US physicists leaving high energy physics as entering it, for reasons that make sense. The budgets fell, for particle physics fell by 50% in 1 year. So those who stayed in the field at all were not, by and large, going to stay in particle physics. So I have a similar question now for this later period. Here's the same plot, PhDs in physics per year. Here's that crash I was showing before. There's a second buildup in the US, this kind of second Cold War, a lot of defense-oriented funding that funds tons of non-classified basic research as well as other projects. And then the Berlin Wall falls, the Soviet Union dissolves, the Cold War ends, you have this fall off a cliff in the fortunes of physics again, symbolized most tellingly by the superconducting supercolliders, enormous hole in the ground in Texas that would have been 3 times larger than the Large Hadron Collider, was in operation, was under construction, and the plug was pulled largely because the Cold War had ended. The reasons to fund a multi-billion-dollar project had changed. So here's inflation-adjusted funding for high-energy physics in the US. And in red, I'm showing when the SSC project was approved. And this, you can again see that when Congress finally voted to kill that, coincidentally 1 month after I entered graduate school, which I chose not to take personally, funding in the US for high-energy physics fell in half in 1 year and then continued to slide against inflation for the rest of the decade. So what happens when a field experiences that kind of rupture? So in blue, I'm showing PhDs per year across all the different divisions of high-energy physics in the United States, theory and experiment. And in green, I'm showing that funding curve, because green means money. And you can see when the money falls, you have a drop by basically 1/3 in the space of a few years in the PhD output, which is, say, the folks who were in grad school, some of them stayed and finished, but they weren't being replaced. There wasn't new recruitment into the field after that very dramatic shock to the system. Now let's go back and overlay citations to the EPR paper. This is meant to be suggestive, not conclusive, right? You have an outflow of very smart people who suddenly have something new to think about, or don't have the old thing to think about. And you have an explosion of interest around the world, of course, not only in the US, in topics like quantum foundations and quantum information. Is that the whole story? Of course not. But is that part of the ingredient to help us make sense of that otherwise very confusing timing about why ideas that had in some sense been percolating for a long time begin to cohere and take off when they do? So maybe to account for these new groups, this new activity, we have to think about core groups and inspiring teachers who could buck a trend, as Wheeler was quite early. We need exciting results like the teleportation protocol. We might need a sort of susceptible population who have reasons to be paying attention now when they might not have otherwise. And of course, we need amazing, ambitious, well-crafted experiments. There's another local IQOQI example, because I couldn't help myself. Very quick coda for the time. So here's a kind of caution for History 4 physics. I overall am excited about the prospects, as I tried to emphasize, but I think we want to do it with our eyes open as well. There's a lovely paper by Peter Gallison from the mid-90s. And he was writing about what were then kind of raucous debates among high-energy theorists about string theory, pro or con. And what Peter pointed out quite in a lovely way is they were having kind of proxy debates about string theory by mobilizing historical arguments. They were crafting what historians would call a usable past. So many string theory proponents would say we're just like the young Albert Einstein. We are sort of bravely, fearlessly following our insights wherever they might lead so that we might better understand space and time at their most fundamental. We have a model from history that we follow, and many string theory detractors thought, oh, you are just like Einstein, but a different example. You're like the old Einstein, who at least in caricature was kind of cut off from mainstream developments in the field, had followed mathematics, sort of blindly in a dead end. So people were fighting about present-day physics by mobilizing distinct historical kind of renderings. And I think we want to be on guard about that when we come to the question of quantum foundations or quantum information as well. This is my last slide here. When it comes to Niels Bohr, he's had very similar fortunes, or he's been mobilized in a wide range of ways as well that we should at least be careful about. There's some otherwise very engaging historical work by Jim Cushing and Mara Beller that, again, many of you might know about. But they're convinced that Bohr was sort of much more troublesome than generative for the history that would follow. They write that basically Bohr was an obscurantist. He was, in a sense, basically a kind of flaming postmodernist avant la lettre, that he was sort of closing down debate, almost like a kind of racketeering charge, a conspiracy not to let things like De Broglie's ideas that would have some similarity to a later Bohm flourish. They're mobilizing a picture of Bohr, partly to kind of score points today about whether they all should be Bohmians or otherwise. And on contrast, actually, this is now, I think, the right way to do it. So I'm giving Chris the last word, again, from this lovely piece that's on the archive. This is the closing paragraph of this very lengthy, very, very rich paper. So let's code a history with a different motivation in mind. I'll just read you his lovely closing. It's good to know who your heroes in physics are, whether they be Bohr, Pauli, Wheeler, or even William James, a psychologist. Their words should not be written in stone. It's not they had all the right answers. But we should think on their words from time to time to set one's agenda and give prod to the imagination, right? To sharpen our questions, not look for all the right answers. Bohr remains a driving force in our quantum thinking and in the fresh field of quantum information, and Cubism thanks him for that as much as anyone else. I think that's a kind of productive way of history for physics, as opposed to engaging in kind of proxy wars by making kind of lessons from the past in a more direct way. So I'll stop there. Thank you.
So we have around half an hour for questions. They can be addressed to both Chris and Kaiser. We encourage also questions that relate to topics and that go in the direction of history for physics, in fact.
Is there a question in here? Chris, do you want to come up?
Just a remark to your slide, to the philosophers, because there you mentioned Mach, and
yes.
Mach was also for 30 years an experimental physicist.
Yes, of course.
He himself did actually more consider him to be a Naturforscher than a philosopher.
Yes, of course. No, Mach is endlessly fascinating. He also, as you may know, had appointments in like surgery, and I mean, he was really a person of extraordinary range. So I'm not trying to say he was only a philosopher, but I think we'd agree he was philosophically engaged and philosophically influential. But not to say he was only doing that. I totally agree.
I have a fundamental ontological question and also a question of understanding for Professor Fuchs.
Good.
Philosopher here. To start with some background in philosophy and within existence, there's the fundamental ontological distinction between real and constructed. By real, I mean something like exists experience independently. By constructed, something like exists experience dependently. Something like observer independently, observer dependently. Now, you mentioned laws of physics in the context of the Wheeler quote. You mentioned law of nature, and in the context of the Perez quote, you mentioned something like exists in nature. The question now is, what's that even supposed to mean? The physical, the natural, is it supposed to be A, real, that's the materialist option? Is it supposed to be B, and that's the idealist option, constructed? is the physical supposed to be both as option 3A, or is the physical supposed to be 3B, and it's probably a more truthful rendering of 3A? Is the answer to that, your answer to that, I haven't made up my mind, I don't know, I don't care? Also because laws of nature can either be laws of noumena or things in themselves, and laws of nature can also be laws of appearances or phenomena, that is laws of constructed. So as a philosopher, I actually don't know what you're talking about, ontologically speaking, because those two are ambiguous terms unless you specify whether you're a materialist or an idealist. Yeah, I think that.
Those were a lot of distinctions. 1, 2, 3A, and 3B. And my mind is not quite capable of capturing all of the distinctions that you proposed. Yes, so is the question, am I a materialist, am I an idealist? Am I somewhere in between?
What does physical mean when you, what the natural, is that supposed to be something real or supposed to be something merely constructed? Also in the case, what does it mean in the case of Wheeler, what does it mean in the case of Perez? Because those are highly ambiguous terms, ontologically speaking.
Yeah. I think what John Wheeler had in mind when he said that the only law of nature is that there is no law of nature, he was thinking that the universe is not a mechanism. And he meant that in a rather deep sense. So I think he was presenting this in a realist account of what he meant by a law of nature, that the universe is not a mechanism. Well, you might have someone like David Lewis come into the story and say, well, the universe is not a mechanism, but it has these chances. And chances are objective things. Or another example is Heisenberg, who spoke of potentia. And the potentia are real in the same sense as the actualities. They're just a different category. But Wheeler, I think, wanted to say that there aren't even objective chances. The world genuinely is, he used the phrase higgledy-piggledy, which you can find in the Oxford English Dictionary, but it's not a word that's used very, very often. So that was Wheeler. Asher Perez, when he said the wave function is not something which exists in nature, I think what he was saying was wave functions exist in the head, in the sense that they're calculational tools. That wasn't the part of my talk that I really got to. Well, I didn't get to it at all. But so there are a couple of distinctions here. One is whether it's fruitful to think of wave functions as living outside of the human mind, as part of the furniture of nature, or whether it's more fruitful, as Perez thought, to think of quantum states as not being out there but in here, calculational tools. Was Perez an idealist? Not at all. He called himself a positivist. In fact, he called himself a recalcitrant positivist. He'd like to tell a story of the first time he met Jim Cushing, who David mentioned in his talk, that he saw Jim Cushing at a conference, and Jim Cushing says, I've been reading your writings, and it's clear that you're a positivist. And Perez said that when Cushing said that, he had the look on his face as if Perez was a cannibal, that it was something so horrific. So, well, anyway, so Wheeler, I think, was thinking in realistic terms about there not being any law. You can try to make sense of that or not. Perez was instead talking about how one should understand quantum states. I don't know how these fit into your categories 1, 2, 3, 4, 1, 2, 3A, and 3B, more than likely, they don't fit into any category. At least I tend to think of myself as not fitting into any category that any philosopher wants to put me into. Because, for instance, I see some features of quantum theory as being instrumental in nature, and a philosopher will say, well, you're just an instrumentalist. I say, hold on. Some things are instrumental. There are other features of the theory that I'd like to think of in realist terms. Which kind of realism? Oh, there are some features that I think of in terms of structural realist terms. There are some features that I think are real in the sense that the American pragmatists, James and Dewey, would talk about. We have the impressions of the real from those things that we can't capture by laws or by predictive statements, but those things that surprise us. So more than likely, my answer just is none of the above, at least for myself. Sure.
First, congratulations for the two wonderful talks. I have one question for Christopher. Wheeler was an inspiration.
Who is speaking somewhere?
Yeah. John Archibald Wheeler was an inspiration for many who entered in the field of foundations of quantum mechanics, including the references you did. But we know now that 20 years or 30 years before you entered in this field, Wheeler also advised somebody, Hugh Everett, to do foundations of quantum mechanics, and Wheeler badly advised Everett to get the blessing from Niels Bohr to his doctoral dissertation, which was, in my point of view, the cause that Everett, in the end of the day, he left physics forever. He never come back to physics. So my question, you probably know this history. What kind of image of Wheeler in which concern foundations of quantum mechanics do you keep of Wheeler? How do you combine these two images of Wheeler? Somebody who badly advises somebody, a young student, to get the blessing from Niels Bohr, or the old guy you knew that inspired and supported young physicists to go in very non-usual manners to approach quantum physics. And for David Kaiser, may you extend a little bit your considerations about pedagogical constraints and just saying a few words about two books which appeared in the 70s. One related to quantum mechanics, the Teil of physics by Capra, and the second not related to quantum mechanics, but I know that you wrote a wonderful paper about the behind the scenes with the book of gravitation by Wheeler, which also suffered this new context from the 70s and 80s, if you have time to.
I'm not. Give him the microphone back, because I'm not quite sure what the question is. So the young Wheeler desperately wanted Bohr's approval of Everett's work.
Yes.
And
yes, that's the question. And in this, I think it was a bad advice.
And the old Wheeler, I think the implication is that the old Wheeler wouldn't have given a damn about what Niels Bohr thought. I don't get that impression. I think in his own mind, he didn't have the live Bohr to consult and get the approval of. But particularly when he made the turn away from Everett's view in about 1968, I believe, 68, 69-ish, he wrote a paper titled "Include the Observer in the Wave Function," and the conclusion was no. And so he turned away from Everett for the most part, though I'm sure you know that they had correspondence even after Wheeler made an information theoretic turn and started thinking about information as being the fundamental stuff of the world. Because if there aren't laws in the realist sense, then what do you have left? Well, at best you've got the information of the things that are floating in that higgledy-piggledy world. But he still, in the end, he was always searching for a way of taking Bohr's phenomena as the foundation of everything. So I don't know, but I imagine he kind of thought Bohr was looking down upon him and would be very approving that it was the phenomena that was the stuff of the world. But I don't know.
Thanks. Thank you, Olival. So I don't want to use up all our time, but so Olival had asked about, on the one hand, the sort of well-selling popular book called The Tao of Physics by Fritjof Capra, and then separately the 1,300-page mammoth textbook on gravitation by Misner, Thorne, and Wheeler, simply called Gravitation. So, and I have written about each of those, and if people are interested, I'd be glad to send you the papers, so I won't spend all the time now talking about them. But I put this slide back up with that question in mind. What really interested me in each of those instances, even though on the surface they look so different, a sort of cheap paperback that's now been sold many millions of times, translated to something like 43 languages, Capra's book, genuinely kind of commercial runaway bestseller. And then this very, very, very sort of intimidating, impressive but intimidating graduate level textbook that you might think of as just different kinds of things, right? Different kinds of books. And what I found so interesting is just how malleable the category of textbook can be, especially in these times of very rapid change. So that's why I emphasized on this slide that I went back to the book reviews of all these textbooks to make sure people at the time in the community said, this is a book to be used for first-year grad students in quantum mechanics, because it's not an ontological feature of the book, right? An inner essence. So very briefly, again, I wrote about the Capra book in my Hippies book is a chapter about it. Capra, as you may know, was a PhD particle theorist who did 2 postdocs, the second of which was at UC Santa Cruz, and it was while in the late 60s. While in Santa Cruz, he was introduced to some of the kind of new age counterculture scene, in his own recollections at least. He went back, his visa ran out, his postdoc expired, he went back to London, out of work, and wanted to write a textbook basically on quantum theory. He loved the subject and wanted to get a teaching job. He thought if he could write a textbook, he might get an advance, because he had no steady paying work at that point, around 1970, 71. So he wanted an advance from the publisher, and he wanted to write a textbook that would put him up better on the job market to get an academic, teaching-related position. So he began writing chapters on explaining at elementary, at a kind of undergraduate level, some core notions from quantum theory and some from relativity as well, actually. Shared them with renowned textbook authors like Vicky Weisskopf. That's where I found the correspondence in Weisskopf's papers at MIT. He recalled sending drafts of chapters to John Wheeler. I didn't look for those very carefully in the Wheeler papers. Maybe you found them. But he was sending chapters to sort of very established textbook authors and senior leading physicists. And at the end of the day, his former postdoc advisor, whom some of you might know, Michael Nauenberg at Santa Cruz, said, why are you beating your head against this sort of textbook project when you have all these sort of earnest interests in Eastern spiritual traditions and so on? Why don't you combine the 2 interests? So Capra has always credited Michael Nauenberg, who's the furthest thing from a hippie, possible, right? That he says it was to Michael's credit. He said, combine these 2 interests. And so Capra went back. The book was rejected by something like, 24 publishing houses, and then it finally came out in 1975 and became this sort of breakaway hit. The point is, parts of it started explicitly as a textbook. How do I explain these things carefully? He had it vetted, or at least, got feedback from people like Weisskopf, because he wanted to get the kind of physics right enough, as well as then explore these other ideas that he'd been so inspired by. And I put this up because when the crash happened, you start seeing in these newer books, say after the crash, formal textbooks written intentionally to be used for first-year PhD students in quantum mechanics. Eisberg and Resnick is one of these, for example, and others. You start seeing in the footnotes references to Copra's book and also to some of the articles in the American Journal of Physics that had been using Copra's book to try to get students back into physics classrooms. Hey, this is actually not all about the kind of military-industrial complex. There are big ideas at the heart of physics. Let's get undergraduates excited about physics again. And indeed, there were like coherent lesson plans on topics like Bell's inequality that had not been in the mainstream textbooks yet. So they get adopted in part just to a limited degree as pedagogical materials, even though they have this kind of weird kind of road to get there. And with the Misner-Thorn-Wheeler book, just even more briefly, that was intended from the start to be a textbook for PhD students in specializing in gravitational physics and general relativity, and they were shocked just before publication that their publisher thought this was going to be a research monograph, not a textbook. And that matters a lot. Are you going to sort of market it to students? Are you going to print it a certain way or binding it? What will it be priced? Will it be priced only for libraries to buy? Will it be accessible, more inexpensive for students? And the authors got very upset, said, no, it's a textbook. They negotiate this whole thing. And the book comes out and indeed was taken up as a textbook in ways we would expect, and then was taken up in curious ways as a kind of popular book. So this 1,300-page brick with multiple typefaces to get all the different tensor quantities distinguished and so on, was actually being reviewed in the Washington Post or some major newspaper like that, as well as a local paper based in San Antonio, Texas, as if everyone should be reading this book. Everyone should read MTW. Can you imagine that? Right? It's crazy. And yet they really had sales that were, the popular magazine Scientific American gave discounts to subscribers to buy MTW, to buy the graduate level textbook, because it had a real market share. It was actually selling to not just PhD students in physics. Partly it was assumed because of Wheeler's famous kind of lyrical style, his use of metaphors and his sort of inspiring language. And so that's an example where the book was meant to be a textbook from the start. It certainly played and continues to play that role. It also had this kind of afterlife. So that's a long way to say what counts as a textbook is not sort of fixed in stone either. And a lot of it comes down to sort of what readers will make of it. And so pairing Capra and MTW I thought was a fun way to think about this moment right around here when what counts as teaching materials is also going in for a kind of a rethink. And I'd be glad to chat more, but that's the quick response, quickish response.
Are there any other questions? So I maybe have one, which is about the history of your physics research. Actually.
Yeah.
So this is the genesis of these cosmological Bell tests. I heard in a talk given by Anton Zeilinger.
Yes.
That these came up with discussions at the Think Shop in physics in this Erische workshop organized in 1976, if I'm not mistaken.
That's right.
Where, a lot has been written about this workshop. Also, Olival has written several stuff, and there's where John Clauser commented that the quantum foundation were finally coming out of the closet, right?
Yes.
Do you know more about the historical genesis of these experiments? Who and how was proposed that?
Right. No, it's a great point. So once we came up with the idea, then we realized, Andy, Jason, and I had worked it out. Then we realized, partly from talking with Anton, in fact, that other people had made frankly, kind of off-the-cuff suggestions along that direction. And we did our best to track down references. In our first paper, we try to cite as many of those as we can. My understanding is that the Eriche conference, which some of you might know much more about than I do, the 1976 one, that this seems to have come up in discussion that was not otherwise transcribed. So we couldn't, at least I couldn't find it in the proceedings. It wasn't part of a formal presentation, but people like Clauser were talking about it, at least in Anton's recollection, at kind of like the coffee break dinner time. But we did find, for example, the philosopher Timothy Maudlin has a kind of, again, a sentence or two in his book from the mid-90s on aspects of quantum entanglement, which we then certainly went back to cite. So we weren't aware of those at the time. And we also, what becomes quite clear is that the community of astrophysicists and cosmologists have learned a lot more about causal structure of space-time since the Big Bang, since the 70s, right? The whole study of cosmic inflation and many, many other things. So the question itself is not the same as it would have been in 1976. Obviously, telescopes and detectors and what it would take to really take real-time microsecond measurements is not the same. So, the short answer is there was an idea that had bubbled up a few times. We did our best to track them down after the fact. But we were wondering about, basically, we came to it from a different path. Yeah.
Thanks. Okay, so, yeah.
Okay, I think this might reveal actually that I'm a bad listener or that I'm tired, but I think I still don't understand this figure. So,
Yeah.
So the last two short answers, percentages, bars that you give.
Mm-hmm.
So I think I don't understand. To my mind, it should be actually the other way around. So the smallest should be last, and the biggest should be. So
Maybe I should explain what short answer means. It's a sort of essay. It's a proxy for writing a mini essay, as opposed to only doing a calculation. Okay, and the idea, as I make sense of this, at least the correlation, if not the cause, is when you have more and more students, you better get them calculating, because that's what you can cover in lecture in an auditorium as opposed to a seminar format. That's what they can hand problem sets in on. That's where you can have a whole machinery to assess, can they solve for Laguerre polynomials or Hermite polynomials, whatever the example is going to be. And then when the classroom sizes fall actually by a factor of 4, because the enrollments fall in half, and in the meantime, the number of departments granting PhDs had doubled in this period. So you really have an enormous shift in the average class size for first-year quantum mechanics. It comes back to being, in many places, a kind of seminar format, as opposed to amphitheater-style lecturing. And indeed, as we can tell from some leftover lecture notes and is written into these newer books, there was a greater emphasis on discussion and not only kind of calculation. So the idea is, what does it take to grade 100 student papers? You don't want 100 essays on Kant. I don't want it, right? No. But if you have 100 papers grappling with Hermite polynomials, okay. You can teach that in a lecture and recitation section. You have a way to assess that. The students can work on it. And I think that's what people like Uhlenbeck were responding to. That's at least how I read this quotation. That if you're teaching them how to calculate, how to make solutions to the Schrödinger equation in a variety of types of situations, different potentials, different boundary conditions, they think they're learning quantum mechanics. They're learning the machinery to calculate with quantum mechanics. And Uhlenbeck, in what was fast becoming a minority of US-based physicists, thought that's not what they need most. So I have that in mind, or likewise when Gurdjieff says, how do you lecture on the kind of more open-ended, unsettled, more philosophically overt questions, and what do you want to get back? You probably don't want 40 or 100 essays, whereas 40 or 100 problem sets, okay, we can staff that up. That's what I read into that. Again, it's not meant to be causal per se. It's sort of it's correlations that sound plausible to me, and then we find other examples like tenure cases, like book reviews, like general exams that seem to bear out that pattern. That's what was on my mind with that. Okay, thanks. Good, thank you.
Could you comment a bit on teaching of quantum mechanics now? So now, I guess it's an undergrad course, but for me, the courses that I had as an undergrad were definitely on the easy to teach side.
Yes.
So if it changed at that point, did it regress?
Yes. I don't know if it regressed. Thank you for the question. So I haven't done nearly as systematic a survey. So I'm going to give you what we can call anecdata, right? Sort of anecdotes dressed as data, masquerading as data, from a very informal survey of the recent textbooks. By recent, I mean published since the early mid-90s, Griffith's textbook, the books that at least in the US market are used most predominantly, most frequent. They all now have at least a chapter on something we might plausibly call quantum foundations. They will talk about EPR and Bell's inequality. They might talk about the measurement problem. They're going to talk about decoherence. There's at least a chapter out of 15 or 20. There used to be 0, so 1 is infinitely larger than 0. It's still small compared to 20 chapters. So I'm certainly not trying to say that this topic has taken over all the textbooks, but I think there's an undeniable way in which that has a kind of a rightful place, even if still a modest one, in the space of textbooks. And when I look at my friends who are teaching, for example, quantum mechanics at MIT and go through the lecture notes again, many of them will start with Bell's inequality to get kids super excited. There's a way in which it's mentioned in the class, even if it's not a class on quantum foundations or quantum information. And again, I imagine we each have different experiences, so that would be interesting to do a more careful transnational comparison and so on. But the upshot is that the new books, as far as I know, each of them has at least some material in it when they didn't used to. Right? Even though in some sense they could have. It doesn't have to be Bell's theorem. They could have had material, even in this period, on measurement problem or other juicy things. Yeah.
Is class size now similar to in the 50s or in the 70s? So is
It went through a real contraction, is now rising. It's rising at a slower pace. So you might think about a kind of adiabatic, like a gas filling. It might be an adiabatic change as opposed to these spikes. Again, at least in the US. So certainly we track obsessively our enrollment patterns at MIT and elsewhere, and the number of majors is rising modestly. So it doesn't look like we're, hopefully it's not this sort of unsustainable push-pull thing, which in the United States we've done twice, if I bring this other one back up. So it's not like this happened in the 70s, we all learned our lesson. There was, an almost carbon copy. I mean, that shape should make us quite nervous, quite humble, I think. Or, we should look at these charts with humility. But indeed, this stops in 2005. My understanding from the latest data, again, in the US-based, is that it's been rising, but at a much more modest pace more recently. But it would be good to get more studies of that.
Okay, we are amazingly on time. And so we conclude the morning session. We will have now a lunch break until 2:30. We reconvene here for the first contributor tandem. Lunch is not provided, but we will downstairs. You can find a list of the suggested recommended places you can find in the area if you're not from Vienna or you're not familiar with the area here. And we reconvene at 2:30. Thank you very much.